Hello. I think everything is ready. Can you hear me? You see the
Yep.
desktop? Okay, great.
Yep.
Okay. I want to pull up the chat window. Excuse me. Okay. Um, so we're going to talk today. We're going to talk a little bit more about binary trees, and I put this is actually a reading assignment I put at the beginning of the semester. Next week we're going to start talking about chapter 2 from the textbook. So we'll switch from talking about binary trees to talking about what's in the textbook about actual stuff about programming languages next week. Okay, so we'll have covered enough about the tree data structure to be ready to start using it to talk about programming languages. Okay, and last night I put up the code that we did in class Tuesday. I forgot to put it up after class on Tuesday. So here's that example we did of the is full recursive method because we did that in class on Tuesday and I forgot to put a link to it up. So I put it up there last night. Okay, and let's see. Oh, let me download the binary tree code. Hey, before going over some more stuff about binary trees, does anybody have any questions about what we did in the last week? Oh, there's a homework assignment. Anybody have any question about first of all, anybody have any question about the homework assignment? Does anything come up about the homework assignment that you are wondering about? Anything about the homework assignment? Okay. What about what about what we've talked about binary trees so far? Does anybody have any question? Anything seem odd or anything seem unusual about what we've talked about so far? Any question yet? Okay. Well, let's go back to the okay. I downloaded the binary tree folder. Okay. Oh, here, let me show you one thing. I was trying to show you how to use JShell on Tuesday, and I don't know what I was doing wrong. I was probably just making typo mistakes because it's actually real straightforward to use. Let me just show you. Like I open a command prompt here. Okay, so I'm in this folder and I type JShell. And as long as you've got Java 11, like I'm using the Amazon Corretto version of Java 11, and it puts itself in the path. So you can just open a prompt and type JShell and JShell will run. Okay. Then I just say open /open to load like the B tree file .java. Okay. So I load the B tree file and then I can start using it. So I can now define a B tree. B equals new B tree. I'll create a B tree with a single node. Okay, so I've got a B tree B. Okay, and I can add a left branch to that. So B dot add left B tree. I think that's the right name for it. I'm going to add a new tree. So I'm adding a left branch to that tree. Oh, see, did I misspell it? Was it just add left tree? I can't remember now. Yeah, it was just add left tree, not add left B tree. I wasn't real consistent about naming these things all the time. Okay, now B is a tree with apples the root, pears the left branch, and it's an empty right branch. And I can add a right tree, B dot add right tree. and I have to create a new tree, new B tree, to add to the right, and I'll add okay, now the tree looks like this. Okay, now for example, suppose I want to pretty print that tree. Okay, if I try to pretty print it, I'll say pretty print dot pretty print. Remember the pretty printer class contains a single static method called pretty print. Okay, so the pretty printer class holds this one static method. Okay, so pretty printer dot pretty print. I can't remember now. How did I spell that with a, yeah, pretty print with a capital P. Okay, pretty print the tree B. Okay. Oh, it didn't like that because I haven't loaded the pretty printer file. Okay, so to use the pretty printer class, I have to keep loading it. Yeah, even though yeah, it doesn't use things until you've actually, it knows that we're in this folder. Because see, it knows that we're in this folder. I can just say open. I don't have to tell it where to find the pretty printer class because it's in this folder. Since I started JShell in this folder, that is the current folder. So when I say open prettyprinter.java, it knows it's in this folder. But it won't look at a file until you open it. Okay. Now if I go back to that line, okay. Now notice it's kind of funny. I called the pretty printer. The pretty printer returns a string. And notice that that's the string returned by the pretty printer. Apple/n, pear/n, green/n. It didn't really pretty print it because the JShell just literally says you returned a string, so that's the string. If I want to actually print that string, I have to do system.out.println. I have to tell the println command to print that string. See, then it gets pretty printed nicely. Okay, so if I just call the pretty printer, the shell says, well, it returned that string. That is literally the string returned by the pretty printer. The pretty printer returns type string. If I want to actually get that string printed in what we usually think of as the usual way, I have to call the print line method, which will then take these /n's and turn them into new lines. Because that's what's in the string. And this is actually what system.out.println does with them. It actually prints them on separate lines. Okay, so notice, but this JShell is real easy to use. I don't know what I was doing the other day. I think I was just mistyping stuff. Okay, here's another thing that's a little bit funny about the JShell that I noticed when I was playing around with it the other day. Suppose I want to build a string from the tree language. Okay, so I want to /open the file build tree. So I want to be able to build a tree. Instead of typing new, I want to be able to use the tree language to just build a tree. Okay. But that one is build B tree. So you notice that if I type a file name and misspell it, it gives me an error message. So that was build B tree. Okay. All right. So now I've loaded that file. Okay. So now I should be able to say something like B tree B2 equals build B tree dot build tree. The build tree method, the build B tree class has one static method that builds a B tree. Okay, it takes in a string and it uses that string as a description of the tree that it should build. And we'll look more carefully at that code today. Okay, but it takes a string representation of the tree and gives me back an actual tree data structure. Okay, so now I misspelled that. That's build B tree. And I want to build a tree that looks like, I'll just build something simple. A with root B, a left branch B, sorry, A with root A with left branch B and right branch C. Okay, so there's a real simple build B tree. Okay, and it didn't work. Now I loaded it, but it didn't work. Okay. Oh, first of all, I misspelled B tree on the left. So let me fix that one. Okay. B tree, B2. Okay. No, so it's still, notice I loaded. Oh, no, I misspelled that one too. Okay. Okay, now it's not misspelled. Am I right? It's not misspelled now. Build B tree. Okay. But I did load it. See, I loaded it, but it didn't work. Here's why it's not working. And it took me a while to figure out what's going on here. The build tree command, this file build tree, it calls something out of the tokenizer. And I haven't loaded the tokenizer yet. So the error is that this file uses this file, and I haven't loaded that file yet. But the JShell doesn't tell you that. Okay, so let me open the tokenizer. Now go back and build that tree. See, it built. What's bizarre is that the error here was that tokenizer hadn't been loaded yet. And it took me a while to figure out what was going on there. That I realized, oh, there was a dependency. That file depended on the tokenizer, and I had to load tokenizer. It didn't say, it didn't say clearly you're not loading the tokenizer and you have to. It just failed on build B tree because build B tree used the tokenizer and the tokenizer wasn't loaded yet. Okay, so that's a little bit flaky on the part of JShell. I don't know if there's a way to make it act better than that. So as long as I load every file I need, then I can, you load them by calling /open. Okay, so you can load all the files you want. Like here's another one. Suppose I want to do a traversal of the tree. Like now I have this tree B2. I can pretty print it. So pretty print B2. See, there's my tree. Okay, now I want to say traverse it. I'll do an in-order traversal of the tree. So I would do traverse dot in order. Oh, I can't remember what it's. So let me look up traverse. Make sure I get the right names for the methods. Okay, I want to do the in order traversal of the tree. Okay, so that's in with a capital O. Okay, so traverse in order B2. But I didn't load, well, I misspelled it. Okay, but I didn't load it yet. So open traverse.java. Now I can, there's the in-order traversal of the tree. There's the pre-order traversal of the tree. And there's the post-order traversal of that tree. Okay, so the tree is root A, B, C. So in-order traversal would traverse B, then A, then C. So in order was B, then A, then C. Left branch, root, right branch. Pre-order traversal would do the left branch. The pre-order traversal would do the root, then the left branch, then the right branch. That gives us A, B, C. And post-order traversal would do the left branch, B, the right branch, C, and then A last. So B, C, A. Okay. All right. Notice I have to load. As long as I load a file, I can just use it in the JShell. Okay. And then I can then go and build another tree. I can build another tree if I wanted to. Instead of this C, I'll put a tree here, D, E, F. Okay, so now A has left branch B, but its right branch is D, E, F. Okay, now I've already declared, I'm going to see what happens here. I've already declared B2. Normally in Java, once you declare a variable once, you can't redeclare it. So I think, well, see, the shell will let you redeclare the variable. Okay, so the shell doesn't quite act always the same way as a Java program would. So it let me redeclare that variable. Okay, and there's pretty printed. See, that's what the tree looks like now. A with a left branch B and a right branch C, D, E, F. Okay. Notice the main use of shells like this is the tester code. Yeah, the main use of a shell is so that you can run little tests on your code. That's mostly what people use shells for, is as a quick way, instead of having to create files and compile them, a shell is a more or less convenient way to run small tests on your code. Okay, so I don't know what I was doing wrong on Tuesday. I did not get the shell to, if I remember right, I didn't get anything to work, and I think I probably was just making typo after typo and not spelling things correctly. And I think I was also mixed up by the fact that even when you load, like when you load this one, it's not going to work until you load all its dependencies. So build tree needed tokenizer loaded also. Okay, so you do have to pay attention. You would think that this thing would tell you that there was a dependency. So if you loaded one file and you hadn't loaded the other one yet, you'd think you'd get an error message saying tokenizer not defined or something like that. But it's just kind of weird, when we loaded build tree but hadn't loaded the tokenizer yet, it complained about build tree not being there. Instead of it complaining about the tokenizer not being there, it complained about this one not being defined. Okay, cannot find symbol build tree. Yeah, even though we had loaded it. So it seems kind of strange the way it's working, but it does work pretty straightforwardly. Okay, I don't know if there's an easier way to do this. Oh, and let me show you another thing that's a little bit interesting about this. Remember, Dr. Java has a interpreter built into it also, a shell. There's a shell built into Dr. Java. But there's this interesting difference between them. The shell built into Dr. Java was put there years ago. So it came before JShell was invented. Okay. The Dr. Java shell came before JShell. Okay. And the way Dr. Java does it is, so for example, if I load this program btree example, well, actually, I'm sorry, close that. If I load btree here, okay, here's the interaction pane. That's where the shell is. If I try to create a btree, undefined class btree. Well, I misspelled it again. Undefined class. Well, it's defined right up here, but it hasn't been compiled. I opened it in the editor, but I haven't compiled it. So if I compile it, so you notice I got the class file here now. Now that I've compiled it, I can go over here. Okay, and there's my tree. Okay, it's got null in it now. Then I can say b equals new b tree. Okay, there's the tree. All right, notice I had to compile it first. And notice that when I compiled it, it created the class file. Okay. Notice that the shell did not create class files. What Dr. Java is doing is that Dr. Java, you don't even really need to have the file open in Dr. Java. You just have to have the class file in this folder. And then Dr. Java's shell reads these class files as you use them. JShell, what's interesting about it is it does its compiling all in memory. So this JShell, it compiled this file and it compiled the pretty printer and the tokenizer, but it compiled them directly into memory. It didn't write anything on the hard drive. So the J shell, the interpreter in the J shell, it compiles your code. Every time you open one of these files, when you open a file, you're actually compiling it. Okay, so if there were compiler errors, you'd get if there was a problem with your file, you'd get compiler errors, but it's compiling them directly into memory. It's not creating class files on the hard drive. Whereas the shell in Dr. Java, which was written a few years ago, it wants the class files in the folder, and then the shell here uses those class files. It uses the class files that are from the hard drive, not the class files that are, it doesn't build them in memory like J shell does. So that's a little bit interesting to see the J shell. It builds everything in its memory. And if you have the class files here, it won't even use them. Well, actually, let's see. I don't think it will. Okay, I'm going to exit the J shell. I forget which command. Yeah, /exit. Okay, I've exited J shell. Okay, now notice I'm in this directory here. So let me start J shell again. I'm kind of curious. I don't think it's going to use the class file, but let's see. Let's see if it's smart. So if I just say something like, now the class file is there. It's in that folder. Eh, it didn't really do it. Notice it created the variable, but see, it cannot be referenced until the class B tree is declared. It's really kind of weird. It's letting you declare the variable, but it doesn't really know what a B tree is yet. So if I say like new B, it really doesn't know about B tree yet. Oh, see, it doesn't know about B tree. It will not look at that class file. I have to open btree.java in the shell. Now okay, so it's going to ignore that class file. So it's designed differently. It's the shell, this J shell, is designed to load all the classes in its own memory. Okay, so it compiles directly into its own memory, and it reads your Java files and builds the class files directly in its memory and doesn't even look at the class files in the folder where it loaded the file from. Whereas Dr. Java is acting more like regular Java programs do. You have to take your Java file, compile it to a class file, then in the shell, which it calls the interactions pane, but it's another, interactions is another word for a shell. In the interactions pane, it will then use the class files. It won't work. Like, I'll go over here now. If I take my tree and I pretty print it, it won't pretty print it because I haven't yet compiled the pretty printer. If I come over here and I load the pretty printer and I compile the pretty printer, now I can go back to the interactions pane. I have to build the tree again. Well, I have to build the tree again. Now I can pretty print it. Okay. So Dr. Java requires you to have compiled the files before you can use the shell on them. Shells are real important. That's why Dr. Java put a shell into itself years ago, and that was actually Dr. Java's claim to fame. Besides being kind of a nice, simple IDE, its real claim to fame for years was that it was like the only Java shell you could get. It was one of the, well, I shouldn't say the only one. It was one of the few Java shells you could get. There were a couple others. I don't know if it's still there. This was one of the first ones. Bean shell. This was a shell written for Java many, many years ago that at one point a lot of people made use of it. And the people at the Java world realized that Bean shell was popular, Dr. Java was popular, and they eventually wrote a shell for Java itself. It was in Java 9 that they finally put a shell in Java itself. But the idea, see, they called it scripting for Java. That was another word for a shell. Yeah, if you could run a language in a shell, it was sometimes referred to as a scripting language. JavaScript runs in a shell. Python runs in a shell. So, scripting is another term for something that can be run interactively in a shell. Okay, so Bean shell was an early shell for Java, and Dr. Java, because the idea is that typing programs in, this is one of the reasons why Python's so popular, because you can just open a Python shell and type Python code. Okay, it's considered good that you can just open a shell and type code without having to create files and compile files and load files. It's just kind of nice to be able to just type code. Okay, so and as we saw the other day, remember somebody said that I should just load the file directly into the J shell instead of opening the files like this. If you wanted to, which is what we kind of work, it's you can actually. So this is not the way people usually do it. You can take that file, copy, and paste it into the shell. And that works too. Okay. But opening it is a much easier. Opening it is a lot nicer than typing the whole class into the shell. But the thing is that this thing requires that it compile the file for you. You can't just compile the file ahead of time, or it has to compile the file for you in the shell. Okay. All right. So the shell it's kind of nice. It is. Shells are considered popular. They're considered a good idea. I mean, it's one of the things that makes Python so popular. And it's one of the things that makes JavaScript popular is the idea that there's a shell that you can just type commands into, that you can just take a file, load it, type commands against it, and just run things interactively. Yeah, the shell is another way to think of it, and that's why they call it the interactions pane. You can use Java interactively over here. Okay. All right. So I wanted to show you, I wanted to clear that up, is that the J shell works fine as long as you first of all type everything carefully. Don't make little misprints. Like I think that's what I was doing the other day. I think I was probably making little typos and not catching them. And also the tricky thing is dependencies. Uh, if you load a file and it uses some other file, it won't necessarily warn you about that. You have to make sure you've loaded all the files you need. Like build tree needed the tokenizer. Build tree, even if I loaded it, it didn't work. Oh, let me show you why I was surprised by that. Let me show you another thing why that kind of surprises me. Okay, here's build tree. Okay, let me load it into Dr. Java. Okay, I've loaded build tree into Dr. Java. Okay, and I'm going to compile it. Now, build tree uses B tree and it uses tokenizer. Okay, when I compile it, notice that compiled B tree automatically and it compiled tokenizer automatically. The Java compiler compiles all dependencies automatically. That's one reason why I was so surprised when J shell didn't load dependencies automatically, because it just seems real weird that the compiler compiles all dependencies automatically, but the shell won't load them automatically. Okay, so like, if I go back here and if I exit the shell and I run the shell again, if I open the build tree, it seems like it's okay, but it isn't usable because it 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 doesn't. I didn't load tokenizer yet. I didn't load B tree yet. So yeah, it isn't like the compiler, which will automatically gather all the dependencies and compile them. Again, you can check if I delete that class file and I delete that class file. Well, actually, if I just click clean, I put that in there to make it easier to get rid of all the class files. You can just type clean and it'll delete all the class files. And you can see again, the compiler, and it's not Dr. Java that's doing this, it's the compiler. When I click compile, Dr. Java just calls the compiler on this file. And then it's the compiler that says, oh, this file needs B tree. So let's compile it. This file needs tokenizer. So let's compile it. Okay. See, so B tree got compiled and the tokenizer got compiled. No, Pretty Printer is not being used yet, so it didn't get compiled. This file did not reference the tokenizer, so it didn't get compiled. So everything this file references, the compiler picks up the dependencies. You would think that the shell would be the same, but it isn't. Yeah, when you load a file into the shell, unless there's something I'm missing that maybe tells it to pick up dependencies. I don't know if that's an option or, but right now, the shell is, it'll load that file and ignore the dependencies, but then you can't use the file until you load all the dependencies. So that's a bit of that's a little bit of a catch that in the shell it's surprising because it's so different than the way the compiler works. Okay. Remember, C compilers and C++ compilers are not smart like Java. C compilers and C++ compilers act kind of like the shell. If you compile a program that has dependencies, they don't get compiled. Like if this was a C program and you compiled this file, that would not compile this and that would not compile this. C programs only compile they only compile the file you're compiling. Because C is an older language. Most modern languages are more like Java now. If a file that you're compiling has dependencies, the dependencies themselves get compiled automatically. Okay? That's a more modern way to do things. And it makes it surprising that the shell doesn't seem to be that way. Okay. But the shell is nice. Shells are very good tools to play around with. They're good tools to learn how to use. Okay, so now, what we've been doing is just playing around with building trees. Okay, so back over here, this is building a tree the hard way. That's what your homework assignment has you doing. Your homework assignment has you building trees the hard way. If somebody gives you a tree, you build it branch by branch by branch. You instantiate the root, and then you instantiate its left branch. You instantiate the left branch, you instantiate the left branch, right branch, you instantiate the roots, right branch. So you have to build all the trees up. Okay, then this is kind of, this isn't very much fun to type this kind of stuff. So then a question becomes, how do you make this better? Okay, and the standard way to make this better is to define a little language for trees. Okay, so we want to define a tree language. That's this thing here. A way of, now this is what we're going to start talking about next week. This is a grammar for a language that describes strings in this language. So a B tree string is a left parentheses, something that represents the root, then a B tree string, another B tree string, followed by close parentheses. So you get things like a left parentheses, something to represent the root, then the string that represents the left branch. So there's the left branch of the apple root, and here's a string that represents the right branch of apple. Well, that's a string in this language. Okay. And if I want to, I can make this more elaborate. I could say, okay, here's the right branch of apple. Okay. There's the right branch of apple. So this tree here is essentially that one there. Yeah, I have a root and a tree that represents the left tree of the root, and I have another tree that represents the right tree of the root. But what's a tree? See, then I recursively say, but a tree is, I go back here, a tree is a left parentheses, blah, blah, blah. Unless I do something like this, then a tree could just be a string by itself. So now this is pair, which is that. So that's the recursion. A B tree is a left parentheses string B tree B tree. Well, this B tree could be what's no, okay, here's another possibility. A tree could be, there's apple with no left tree and a right tree, because that is a tree being string, that's apple, an empty left tree, and then a tree. Now, what's that tree? That tree is, well, that tree is string, this one here. See, that one used recursion. So this part up to here was from here. And then I use recursion to pick up this part here, which is that thing there. And if I want to, I could. Now, how's that tree being built? Well, a tree is, I'm using this line here. It's a root, an empty left branch, and a tree. That's this one recursively, where this tree is now using this line here. On your hand, I could do that. Now, the tree is this. I'm sorry, it's this line here because it's a root, a empty left branch, and a tree recursively. That's this guy. But then this guy recursively is using this line here because it's a root, a left branch, and an empty right branch. And the left branch is using this one because it's just a single node. Okay, so I'm using 3 levels of recursion here. The top level, which is one of these, then a level down, which is one of these, and then a third level in here, which is one of those. And this is what the next chapter, this is what the first chapter of the book is about, is we're going to spend a lot of time talking about how to read a grammar and use a grammar to build strings in our language. Okay, now once I've got this idea of I can represent trees, I want to write a program that takes a string from that language and actually builds the tree for me, so that I don't have to type all those new. Remember, what we're trying to do is get away from doing this. Yeah, we'd like to be able to not have to do all that to build a tree. Okay, so once I've defined the tree language and I write this program that builds trees, then I can do the following. I can say, here's a string in the tree language. That's the string that represents this big tree here. I can just say, build a tree from that string, and then this one line replaces all that. See, there was the construction of the tree. Now the construction of the tree is done essentially automatically for me by this guy using that string to represent the tree. And this is a real powerful idea in computer science. This is using strings to represent data structures. Okay, now that's part of programming language theory, but it's using what do we mean by using strings to represent data structures? Here's another way to think about that. I can't remember if I don't think we did this in class. I don't remember if we did this. In Java, you can say int a, you can create an array. there's an array of 4, right? And then I can put things in the array. A0 is, say, 21. A1 is 22. A3 is 24. And A4 is, say, 25. Okay, so I created a tree, I created an array, which is a data structure, and I put something in it. Okay, but you probably know that there's a shortcut to that. I can say int A equals curly brace 21, 22, 23, 24. Okay, now what is this? This is what we call an array literal. From our point of view, what's the connection between what we were talking about a minute ago and this? What's the connection? Think about it. See, what's the connection between this guy and this? The real important idea, I want you to think about, what did that line of code do there? If I want, I can even take this string, put it right there. Compare that to that. What do they have in common? Okay, somebody said that, okay, say it out. What do you mean it's a simplified way of setting up a tree array? Okay, that's a little bit vague. What do you mean a setting up? What are better words to use? Setting up's not a programming term.
Constructing.
Constructing. Yeah, you construct objects. Okay. This constructs an array object for me and initializes it automatically. It constructs the object using a little bit of a string length. See, it's like a string representation of all this. Now, what we call it is a literal. We call it an array literal. Okay? An array literal is a nice way to describe a data structure. That's what I've created over here. I've created a tree literal. But I've created it, it's not built into the Java language. I'm essentially building it into the language. Now, Java only has array. The only literal data structure Java lets you type is an array literal. Java doesn't have literals for other kinds of data structures. This is actually kind of a problem in the Java language. The only data structure it has a literal for is arrays. Okay. And here we're essentially putting into the language an array, a tree literal. And the literal is going to be a string representation of the tree. But notice that now I can build the tree by typing in essentially a literal representation. Okay. To give you a sense of why this is important is other languages do this better. The most famous example of what we're talking about is JSON, the JavaScript object notation. JavaScript has a very powerful literal language built into it. Okay. In JavaScript, you can describe, okay, that's the grammar for the JSON language. We'll talk about it in a little bit later, but let me just get some JSON examples.
Wait, isn't JSON just an alternative to XML?
No, it's a replacement for, well, yeah, well, don't say just. To say just a replacement for XML is, is belittling it. Um, XML and JSON are languages for describing literal data structures. It's an alternative to XML. So there are two different commonly used languages for literally describing data structures, XML and JSON. Okay, but what's the difference between JSON and XML? The big difference is that JSON's built into the JavaScript language, XML isn't. So if you want to use XML to build a data structure, you have to do like what we're doing here. You have to write a program that builds the data structure from the XML. JSON is more like what we're doing here. JSON's like this array literal is built into the Java language. JSON is built into the JavaScript language. So JavaScript has, so for example, see this? Notice it looks a little bit like an array literal. It starts with a curly brace, but that builds an object. It doesn't build an array, it builds an object. And there's a bunch of other examples like that. You have to learn how to read JSON, but what JSON is, it's a language built into JavaScript that lets you literally build data structures. For example, you can build trees with it. You can use JSON in the JavaScript language. We could build our trees using JSON if we wanted to. We could build trees by typing a JSON string. Well, actually, it's not a string. Notice that the JSON is not a string. It's part of the language. Okay. It's part of the language. Okay. So see, JavaScript has a literal notation that's very powerful. Java has a literal notation that's very limited. It only lets you describe arrays. It doesn't work for anything but arrays. So you can't describe objects in lit. The only way you can get objects in Java is to type new and actually call a constructor. Okay. So what we're doing is we're essentially adding a feature to the Java. One way to think about this is we're adding something to the Java language. We're giving the language the ability to let us literally describe a tree, but we have to write a program that does that for us. Okay. So we're adding to the Java language the ability to conveniently describe tree data structures. And this is done this is not an unusual thing to do. Sometimes people call this a domain-specific language. We're adding a language to a language. We're adding this little language here to the Java language. We're essentially augmenting Java with a little language. Okay, and people refer to it as DSLs. I mean, if you go here and you here I'm getting domains, digital subscriber loop, which is a way of internet connecting to the internet. Let's see. I'm surprised it's not showing up here. A real common, the DSL abbreviation. Domain-specific languages, DSLs. It's a very important part of computer science. Okay, and this is kind of one of the ideas that we're building up to. Notice that they're called mini languages. Okay, what we're doing is we're adding a mini language, a DSL, to Java, and it's our tree language. Our tree language, we're essentially building into Java a little mini language that lets us describe trees. Okay, so we're building a DSL into Java. Okay, and our build tree, this thing is the language. This is the thing that translates the language expressions into it takes the language expressions and gives us back tree objects. Okay, takes language expressions and builds tree objects for us. Okay, that's an example of using a domain-specific language. It's not, there's lots of reasons why you might want domain-specific languages. Here we're using it to describe data structures, like JSON. JSON is a little language built into JavaScript that describes objects in JavaScript. And JSON is a syntax. It's a language for storing and exchanging data. Okay. And here's the web page, here's the home page for JSON. There's the grammar for JSON. That's a grammar like we wrote a grammar for this tree language. We'll learn how to, we'll go back to that one in a little while and read it and see that this thing here and this here are the same things. They're a grammar. This language is more, this is a more complicated language than our little baby tree language. So it's got a bigger grammar to it. Okay. And these pictures over here are another way of describing the grammar. These pictures over here are another way. Oops. These are two different ways of describing a language. This is a grammar, and these are called train track diagrams. So we'll come back to these later. But these things on the left are redundant with these things on the right. Two ways of describing a language. Okay. So JSON's a domain-specific language for building data structures. It's a syntax for data. We're building a syntax for trees into Java. There's our syntax for trees. Java has built into it a syntax for arrays, but nothing else. They don't give you a syntax for anything but arrays. Okay. C++ actually has a syntax for C++ does have a literal language for objects. Okay. C++ does have a literal language for trees. Okay. And we're not going to go into it now, but you can build more than arrays in C++. You can build, you can use this notation in C++ to build objects. Okay. But not in Java. Java the only literal that Java has is array literals. If you want any other kind of literal, you got to build it yourself, like what we're doing, building a language for trees. Then we can build trees real easily. You type a string in that language and you get the nice tree. Okay. And then there's like a whole bunch of examples in another file. That builds a tree, that builds another tree, that builds a different tree. So each one of those is a language, each one of those is a string in our baby language of trees, and each one builds a tree. And we see we're going to loop through that array of strings and build a tree from each string. And build a tree from each string. Okay. Now right now we're not going to talk about how we build a tree. We'll come back to this later on. Okay, the code here is not trivial code. Yeah, it's not a lot of code, but we'll come back to it after we've talked a little bit more about what's in the textbook and we've studied a little bit more about languages. Then we'll come back and actually look at the details of how this build tree works. Okay, but build tree is an example. It's an example of a parser. Okay, so this is a parsing program. It parses the string and builds the tree. Okay, and like, for example, go back to the JSON language. The JSON language is built into JavaScript. What about Python? JSON is not built into Python, but people in the Python world use JSON. So what people have done is they've written parsers for Python that read strings in the JSON language and build Python data structures. Okay, so in the Python world, they've written a build JSON. People have written libraries that do essentially build JSON that take strings in the JSON language and give you back Python data structures. So they had to write the code for that. So somebody wrote that. Actually, there's a whole bunch of people who've written it. Different people have written different versions of it. Okay, so JSON is built into the JavaScript language, but it's not built into the Python language. And JSON has become popular enough that there are JSON libraries for Java too. I'm not sure. Let's see. I don't think it's built in. I think you have to download it separately. It's not part of the Java standard library, as far as I know. So you have to download somebody's things. Okay, see, so I'm just looking for a good example. Yeah, see this string here. That string actually describes something in the JSON language, and then you parse it, and you get an object. See, so you would take that string, use this library's parser, and that would turn it into an object. Okay, and that's the kind of thing where so in the case of Java, you can work with JSON, but you have it's not. I don't. At some point, it might become part of the standard Java library, but it's not part of the standard Java library unless there. I don't think it is yet. I don't think there is a. I think you have to download somebody's JSON library. Yeah, see here he mentions there's 4 different libraries. The most common JSON libraries for Java. Yeah, I'm surprised. At this point, JSON is so popular. I'm surprised that JSON hasn't finally moved into the Java standard library, but it doesn't seem to yet. So you download other people's library. So those people wrote programs very much like our build tree. Our build tree that we're going to learn how to work with here. It takes our strings in this baby tree language and builds us Java tree data structures. Okay, and this has become very big. This is a very big part of programming these days. Being able to describe a data structure in a string and then building the data structure in memory from the string is real important. And there are 2 standard ways of doing that are XML and JSON right now. And XML came first and JSON came second. And JSON is much more popular now than XML is. XML is still used by a lot of people, but if people are starting new projects these days, they're probably more likely to choose JSON over XML. But if people are working with an older project, they might just be stuck with XML. Okay, so XML is a language for describing data structures, and JSON is a language for describing data structures. You write a parser that takes a string in that language, and it will build the data structure for you. That way you can now why would you do that? Why will we want strings? Why do we want data structures as strings? They may have a sense of what's the point? Why have JSON?
You can load objects dynamically.
Pardon me?
You can load objects dynamically
From where?
from like text or through the network or
Right. Yeah, it's a lot easier to download a text file over the internet than it is to download some sort of weird binary object file. Okay. If you want to send an object from one computer to the next, it's a heck of a lot easier to make it a string and send the string over the internet. And then the other computer that's receiving the object can parse the string and rebuild the object. So in our case, what if I had a tree, I would take the tree and I pretty print it. The pretty printing turns it into a string. Then I could send that string to somebody. Then they can take that string and parse it and build the object back. So we could communicate objects between us. I have my object in my computer's memory. I pretty print it to a string, send your program the string. Your program parses the string and rebuilds the object. That's a heck of a lot easier than me somehow sending the binary data structure over the internet. It's hard to send binary data structures over the internet. They're a little bit tricky to do. So it's much more common to want to send a string representation over the internet. That's what made XML and JSON so popular. It's way easier to send strings over the internet or to store them in files. It's way easier to store strings over the internet, to store strings in file, or to send strings over the internet and let somebody rebuild the data structure from the string. Okay, so that's what people do with JSON. They store JSON, they store data in JSON strings, send those back and forth over the internet, and then when they need the object, they parse the string and build the object. Then they can process the object and then maybe pretty print it back into a string. Then that could be put into a database, or it could be sent to some other program. And that's become a very common way for programs to work now. They send data back and forth using the JSON or XML. I mean, they're both still pretty popular, using the JSON, using either JSON or XML is a lot more complicated than JSON. That's one reason why people got like JSON a lot better. XML is a big language. JSON's a little language. This is the whole description of JSON. That's little. That's a very small language. XML is actually quite a large language. It has a lot of features. Okay, takes a lot to describe XML. Okay, so XML turned out to be overkill. XML is more than what most people wanted. So XML is overkill for a lot of uses. JSON's kind of like a sweet spot. It's complicated enough to be able to do a lot of work, but it's still fairly simple. So a lot of people realized that JSON was just right for them. It could describe fairly complicated data structures, not as complicated as XML. XML can describe more complicated data structures, but you rarely need the full power of XML. So JSON turned out to be good enough for almost everybody. Okay, and the funny thing was that JSON was built into JavaScript, and there was one guy who actually figured this out. He looked at JavaScript. The guy who wrote this web page, this was done many years ago. He looked at JavaScript and said, there's a language inside JavaScript that everybody should be using for describing data structures. So he essentially extracted from the JavaScript language this JSON language and said, here's a little subset of JavaScript that we should all be using as a data language. And then he called it JSON for JavaScript object notation, and it became real popular. But he basically pulled a piece of the JavaScript language out of JavaScript and turned it into a baby language. Okay, it's actually, it was a real interesting thing. It was a really clever idea. It made him real famous. This idea made this guy really famous. Okay, his name is Douglas Crawford. This is the guy who did it. Okay, it's this guy here. Okay, he became real famous for this one great idea that there was buried in JavaScript a language that was really useful for describing data. And he basically used that to replace XML. Okay, so it was originally part of JavaScript, and he pulled it out of JavaScript and made it its own language and gave it a grammar, like we have a grammar here for our tree language. We have a grammar for our tree language, and we're going to start learning about grammars in general. This is a baby language for describing a simple data structure. JSON is a baby language for describing slightly more complicated data structures. Eventually, we'll see that we can describe all of Java and JavaScript using a grammar. There's a huge grammar that describes all of JavaScript. This is just a small piece of the JavaScript grammar. Like if I go here and I type, see if I get the whole grammar. I thought I would get the JavaScript grammar real quick. Oh, there's the grammar for JavaScript. That's actually not even all of it. That's part of it. See, we're going to learn how to read these things. Okay. We're going to learn how to read, but this is a grammar for JavaScript. And you click on these, it gives you more grammar, and you get, okay. All right. So we're going to learn how to read. Now that's a lot larger than the grammar for Java. For somewhere in this page is the sub language that would be JSON. This is the grammar for all of JavaScript. And more or less somewhere inside of there is the little part that this one guy pulled out of it and said, this part of the grammar is a nice language for describing data. Okay. All right. So now we're actually taking, this is a course on programming languages, but what a lot of people realize that languages don't describe just programs, languages describe data too. And that's just as important a part of this. Just like over here, essentially, this is a little language for describing arrays, and it's part of the Java language, okay? And there's kind of a circular thing to it. A language that describes data structures can also describe programs. We're going to see that programs themselves are data structures. So eventually we'll see how this kind of like, it's very circular. Programs describe data structures, and data structures are programs, okay? So we'll see how this works out, but it's essentially buried in JavaScript and Java are little languages for describing data structures, and we describe programming languages as data structures. Okay? So what we need to do is we need to learn exactly what a grammar is. Okay, that's the first couple chapters of our textbook. What exactly we mean by a language and a grammar. Okay. Then when once we know exactly what we mean by a language and a grammar, we'll go back and see how we can parse grammars to build objects, and we'll see how that can be used to represent programming languages in interpreters and compilers. We'll use parsing of strings to build programs in interpreters and compilers. Okay, all right. Now, go back over here. Essentially, that is the data structure that describes a tree. That is a language we can use for representing tree data structures. And then this program takes strings in that language and builds data structures of that type. Okay, so that's the logic of it. Okay. Data structures, a language that describes those data structures, and then a program that can take strings in that data structure, strings in that language, and build that data structure. Then a couple of examples, and then, the build tree needs this thing called a tokenizer. Okay. Now, what's the pretty printer? The pretty printer goes the other way. The pretty printer takes a tree data structure and gives us the string that represents it. That would be the string we could send to people to say, here's the string, you can rebuild the data structure yourself. Okay, so this is sort of, pretty printer is the opposite of this build tree. Build tree takes the string, builds the data structure. Pretty printer takes the data structure, gives us the string. In fact, in the world of programming languages, pretty printers are sometimes called unparsers. This one's a parser. This is an unparser. Okay, so sometimes you'll if you play enough or with this, you'll see that pretty printers are sometimes referred to as unparsers. Parsers take strings and build data structures. Unparsers take data structures and write them as strings. Okay, string, data structure to string. Okay, you can go either way. Start with a data structure, turn it into a string, start with a string, and turn it into a data structure. And this guy tells us what the strings look like. What are valid strings? Okay, so, and we need a tokenizer. We'll talk about it. Tokenizers, in the process of building the tree from the string, you need something called tokenizing. We'll say more about what that is. So that's like a little minor step that starts the process of taking the string and building the tree data structure from the string. Okay, so JSON would be a language like this. Then you could have a build JSON data structure that would take strings in the JSON language and build data structures. And you would have something that pretty prints JSON that could take a JSON data structure and write it out as a string that you could send to somebody. Okay. Okay. So that's kind of the flow of this code here. Remember, strings and data structures. Strings that represent the data structures. Okay. The string is a convenient way to represent the data structure. And sometimes we call those literals, just like here, a string that conveniently represents all that. Well, it represents that. Build the array and put things in it. This builds the array and puts things in it in a lot less code. Okay. And that's what we're doing in our tree. We're over here. That's a lot less to type than all that. That there is the equivalent of building the array the long way. Okay? And this is the equivalent of building the tree from the literal. Okay? So that's the kind of thing we're going to be talking about more and more. A representation for the data structure versus the data structure itself. A representation versus the data structure itself. Okay. One last thing I'm going to put up. We didn't get to it. These trees that we need, they always hold a string in the root. But if you go back to the data structures class, why does a tree always have to have a string? Why couldn't a tree hold integers in the root or doubles in the root? So that would require you to have a generic tree. So I wrote a version of the tree that's generic. We don't need it for this class because we're working with strings. So we're really going to work with trees of strings because we're working with languages. But it's nice to see that you can write a generic tree that lets you store anything in the root. So this is what trees would look like if they were generic. I haven't put this up on the website yet. I'll put it up after class. And then there's an example in here that builds two trees, one tree with strings and one tree with integers. So here's building a tree with ints in the roots, or with strings in the root. And then here is building a tree of integers. And then I could build a tree of doubles. I could build a tree of trees. I could build a tree of trees if I wanted to. Okay? So, from the point of view of the data structures course, you should define generic data types. We don't need a fully generic B tree for this course. So we'll stick with a simple B tree where it only stores strings, but it's nice to see that you could write a generic B tree. And that's what that's what Java would probably do if there was a B tree in the Java language, it would be a generic one. Okay. All right. So we come to the end, run out of time. Next week, we're going to turn to the textbook and really start talking about languages and grammars. We're going to make really precise what we mean by this thing being a grammar. We'll learn how to read, for example, this JSON grammar and this other version, this other way of writing a grammar. And we'll see that, and then we'll talk about what's called parsers. The general idea of taking a grammar and using it to build data structures. In general, how do you take strings from a grammar and use them to build data structures? That's called parsing. So that's what we're going to do for the next couple of weeks. And we'll be making use of trees all along, but we'll start talking less about trees and more about grammars and parsers. We've covered everything we need to know about trees, and then we'll start just really talking about the grammar and the parser part. Okay, so run out of time. If you have any questions, I have office hours this afternoon, And also there's, if you have, you can send me email, especially about the homework assignment. If you have questions about the homework assignment, send me an email or come to office hours. Okay? Any question about, before we quit, any question about today? Anything? Okay, I'll put the generic B tree up on the course website. So if you want to look at that class, it's a minor change to the code. And like I said, we won't need it in this class because our trees will always be holding strings. Because we're working with languages, we only need trees that hold strings. We don't need trees that hold other kinds of data structures. But it's just nice to see that they can be done that way. Okay, so I'll go ahead and stop sharing and have a nice weekend and see you next week. Bye-bye.